Hi guys, I'm making this video just to help you get this in for the 15th of April. Just trying to do all the past work as much as possible. I've just listened to my own voice. It is pretty tragic, so you're just going to have to grin and bear that. The first section here is on naming compounds, and it's quite easy. All you've got to think of first is count the longest chain, the longest carbon chain, and then name it. So we've got a little table here for, oops, the wrong thing on, little table here for the number of carbons, 1 carbon, 2 carbon, 3, 4, 5, so methese, prop, bute, pent, hex, hep, dot, non, and dec. So I'm going to give an example now. I'm going to give an example of this one up here. First off, what we've got to do is count the longest chain, so 1, 2, 3, 4, 5, 6, 7. So that's 7, and we'll count alternate chains. 1, 2, 3, 4, 5, 6, 7. Yeah, so they're all 7. 1, 2, 3, 4, 5, 6. So 7's the longest, so this one's going to be called hept. It's got no other functional groups on it, it's just CHs, so it's going to be an alkane. So it's going to be heptane. But we've got a couple of side chains on there. We've got 1, 2 side chains. So these are single carbon side chains, so they're going to be called methyls. Single carbon side chains are methyls. If there was 2 carbons on a side chain, it'd be called ethyl. And if there was 3 carbons on the side chain, it would be called propyl. And 4 would be butyl. So this is single carbon side chains, these ones here. And now what we've got to look at is at what position do they come on, and we're looking for the lowest number. So 1, 2, 3, 4 from this side, and 1, 2, 3, 4, 5 from that side. So we're going to approach it from this side. So we've got 1, 2, 3, 3, 4, and we've got to put in there di, because there's 2 of them, methyl heptane. So this is 3,4-dimethyl heptane. Next one, very easy, single straight chain, 1, 2, 3, 4, 5, 6, 7. So this is just pure heptane. Next one along, 1, 2, 3, 4. So 4 carbons, we're going to say it's a butane. And it's got a side chain on there. It's got a single carbon side chain here, so it's a methyl. So it's 1, 2. So this would be 2-methyl butane. Nice simple one here. 1, 2, 3, 4 butane. I'll leave you to find this one out yourself. Now we've got an interesting little character here. This is a ring structure, so we've got 1 ring structure here, 1 ring structure there, and another ring structure there. Now these are just straight chain ring structures, no double bonds. These are called cyclo. Whenever it's in a ring, it's called cyclo. And it's just a normal alkane, so all you need to do is count the number of carbons and then call it cyclo. So for example, 1, 2, 3 carbons would be called cyclopropane. Okay, so I hope that is going to help you with that first section, and you've only got a couple more to name. I just want to run through here the benzenes. You've got some benzene groups here. Whenever it's got this ring, excuse my drawings here. Whenever it's got this hexagon ring with the triple bond like this, it's called an arene, or benzene chemistry. Okay, and the first and most simplest one, this ring with no attachments, is called a benzene, and then it goes on from there. As you add attachments, you you call them different names. So, for example, this one here has a bromine attached, but when we're talking in organic chemistry, a bromine is labelled bromo. So this would be called bromobenzene. Okay. This NO2 is a nitro group. So this is called, I'll leave you to find that one out. And this one has got two nitro groups on, and so is therefore a dinitro. Okay, so I didn't want to give you all the answers, but I just wanted to run through the basics for you, so you can go through now and adjust accordingly. Okay, so try and answer those. I just wanted to have an interval where I just talked about some of the functional groups, the carbonyl functional groups. This one here, as you can imagine, it's got two R groups, and those R groups could be anything. Because it's mid-chain, it's called a ketone. And its suffix is own. I'm sorry about that, guys. The Doodlecast just shut down. So this is a ketone. The next one here, so I'm going to underline. Actually, I'm going to change my colour for a little bit. I'm going to go to blue. The next one here is an terminal chain carbonyl group. So C double bond O here on a terminal chain. So it's got, we know it's terminal because it's got a hydrogen at the end. So this is an aldehyde. Sorry about this writing, hold on. So this is an aldehyde. And it ends with al. This one here, terminal again, but this time it's got a chlorine at the end. So this is called a thionyl chloride, an acyl chloride, sorry, and this ends with oyl chloride. So that's an acyl chloride. Here, this is the next one here. We could imagine two R groups here. So these could be any size carbon chain. This is carbonyl attached to an oxygen. So, and then it's got two R groups attached here. So this is called an ester. And we've been through naming esters. So go back and check your notes, and yeah, you'll be fine. This one is a bit like an ester. However, it's got two carbonyl groups attached to this central oxygen, and this is called an anhydride. And I think we went through this extensively. So go back and look through your notes again. But these are called anhydrides. If you're looking on the internet, then at least you'll know. The next set are double bonds. So I'm just going to draw in a couple of R groups there just to make it easier. These are called alkenes, and they end with E. The next group, I'm just going to draw in. So I've drawn in two R groups here. This is an alkyne, and ends in -ine. So we're going to use this information to move on to our next slide. So we've got all of the alkynes, alkenes, and ketones, and carbonyls, and aldehydes, and everything else here. And I'll just run through one example of a ketone, one example of an aldehyde, and one example of an ester. So here, we'll take this first one. Same as usual. First off, we know that it's a ketone because we've got that carbonyl mid-chain. But first we need to count the number of carbons. So 1, 2, 3, 4, 5, 6, 7 carbons. So it's going to be hept. It's a ketone because it's got a mid-chain carbonyl, so it's heptanone. And that's it. We've named it. Heptanone. Okay. The next one is an ester. We know it's an ester because we've got a carbon here, carbonyl, oxygen, and then another chain there, so another R group there. So first off, what we need to do is name the alcohol portion first. So the alcohol portion is always this portion. So we count the number of carbons. 1, 2, 3, 4. So 4 carbon chain would be bute. Okay, so this is butyl. Oops, spelled that wrong. This is butyl. And then we count the carboxylic acid portion, which is this portion here, and I'm just going to change colour just to help. So we count the number of carbons. 1, 2. So this is butyl ethanoate. Okay, so that's what you do. Every single time you do an ester, do exactly the same thing. Count the straight chain portion first, and then count the carboxylic acid portion, and name it like that. Okay, so this, we've done a heptanone, we've done butyl ethanoate. Let's have a look at this guy here. This is an aldehyde. Count the number of carbons first, so 1, 2, 3, so it's prop. It's an aldehyde, so it's propanal. Propanal. Let's have a look. Let's go for an acyl chloride, which is this one here. Count the number of carbons. 1, 2, 3. Propyl chloride. Propanyl chloride. Okay, so that's pretty easy. And we'll go for an alkene. There was our alkene. 1, 2, 3, 4. So it's bute. It's an alkene, but we want to count the position. It's in the 1, 2 position, so it's bute 2-ene. I think we'll call it a day on that one. Okay, that's the naming section. There's some haloalkanes here, so this would be a 1, 2, 3, 4, 5 carbon, so it's pent, but it's got an iodine group attached there, so this would be iodopentane. Sorry about the writing, but it's iodopentane. And if you've got 2 of them, you count the chain. 1, 2, 3, 4, 5, 6. So this would be hexane. We've got a couple of additions here, so we've got bromo and a chloro. So 1, 2, 3, 4. So it'd be 2, 4, 2. Sorry, got that wrong. We'll do it. This would be 4 bromo. 2 chloro, hexane. So 4 bromo, 2 chloro, hexane. 2 because it's in the 2 position, 4 because this is in the 4 position. Count from the smallest chain. 1, 2, 3, 4, 5, 6. So 4 bromo, 2 chloro, hexane. Alphabetical order. Right, cheers guys. Okay, we're on to this next section of the assignment. This is exactly the same, but in reverse now. So we've got the names of certain compounds, and what we need to do is just in reverse draw the structures. So for the first one, it's 1 chloro. So we know that the chlorine is going to be in the 1 position. 1 chloro butan 1-ol. So the main chain here is a butane chain. So we can draw a butane. 1, 2, 3, 4. In the 1 position, which is here, there's going to be an alcohol. And in the 1 position, there is all. So we've got the 1 position for the chlorine, the 1 position for the alcohol. So that's 1 chloro, 1 chloro, butan 1-ol. Next one is 2-methyl. So there's going to be a methyl chain, a CH3, hanging off in the 2 position. 2-methyl butan 1-ol. Well, that's easy because we know that we've got a butane chain. Oops, I've done 2, 1, 2, 3, 4. There's my butane chain, and then there's my alcohol. So that's 1, 2, 3, 4. Butan 1-ol. And in the 2 position, we need to add a methyl group. So 1, 2, there's our methyl group. And remember, we don't have to write CH3. I mean, you can do if you want to. Or you could write Me, which is the same thing. Okay. Next one is 2-bromopentane. So pentane chain 1, 2, 3, 4, 5. There's your pentane chain. And in the 2 position, 1, 2, there's a bromine. So not too bad. I'll leave you to finish the rest. On this one, this was name primary, secondary and tertiary for the alcohols, amines and haloalkanes. So I'll start off with the alcohol first. If you've just got an R group, like that, 1 R group attached to the alcohol, that's primary. If you have 2 R groups attached to the carbon that the alcohol is attached to, that's secondary. And if you have 3, that's tertiary. So primary, secondary, tertiary. And that's exactly the same for the haloalkanes as well. I'm just going to draw for bromo here. Primary bromo, secondary, tertiary. For this section, you just need to name the primary, secondary and tertiary. Now, alcohols and the haloalkanes, they're all the same. You're just counting number of carbon chains. So I'm going to draw them together. They're both primary because only 1 group is attached to this carbon, 1 R group. If we've got 2 R groups attached to the carbon, the alcohol, or the carbon that the bromine is attached to, then that would be secondary. So this is primary, this is secondary. If we've got 3 groups attached, then this would be tertiary. And we can draw a tertiary haloalkane. So you're just looking at how many groups are attached to the carbon that either the alcohol or the haloalkane is attached to. So for example, nice and easy, this has got, there's the carbon it's attached to, there's only 1 group, this group here, so that's a primary. Okay, so you go ahead and have a look at the rest of them. So 1, 2, so there's only 2 there, so go and have a look at those. With the amines, it's slightly different. Primary amine looks like this. That's primary. Okay, so but what we're looking at now is number of carbons attached to this nitrogen group here. So what you've got here is 1 carbon chain attached to this nitrogen. I'm drawing it like this on purpose. Okay, now NH, this little setup here, now there's 2 carbon chains, this carbon chain and this carbon chain attached to the nitrogen, so this would be a secondary amine. And the last example would be nitrogen. Now there is 3 carbons, 1, 2, well I'll draw 2, and 3 carbon chains attached to that nitrogen there, so this would make it tertiary. So just think about that. The better way to do it is to count the number of hydrogens on the nitrogen here. If there's 2, then it's primary. If there's 1, it's secondary. And if there's none, it's tertiary. Don't fall into the trap. Okay, so that was just to help you out there with the namings and the identifying. So you go and have ahead and have a go at them. The next little thing that we need to do is look at these isomers. Now isomers, this is C5H12, so let's go at 1, 2, 3, 4, 5, and how many hydrogens? 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's our first isomer, let's see, 5H12. The next thing is we could draw 4 carbons. So basically, you've got to use all the carbons and hydrogens. Same formula, but different structure. So could we get away with putting a methyl group there? So I'm just going to draw it like this now, just to make it easier. So we've got, this would be a CH3 as well, because it's terminal. So 3, 4, 5, 6, 7. Oh no, this would be CH, wouldn't it? 1, 2, 3, 4, so that's CH. 3, 4, 5, 6, 9, 12. So now we've got pentane, okay, and we've got 2-methyl butane. Same molecular formula, C5H12, but different structure now. So it's a structural isomer. You need to go through and find out how many structural isomers, and draw them all, there are for C5H12. Have a go at drawing them yourself first, but there is a web link that I put on there for you, so that would be really useful. This next section is on chiral compounds. Now chiral compounds are easy, they're just mirror images. And the first thing you're looking for in a chiral compound is, does it have 4 different groups? So does it have 4 different groups attached to the central carbon atom? So I'm going to draw an example here. This would be an example of a chiral carbon atom. If I draw an extra line on there. We have got a chlorine, a hydrogen, an ethyl 2-carbon unit, and a methyl group, a 1-carbon unit. So it's got 4 different types, 4 different groups attached to this central carbon atom here. So this would be chiral. Okay, so you're looking for 4 unique groups. Let me give you an example of something that is not chiral, and it would be this one here. For a start off, we've got a chlorine. That's good. Next, we've got a bromine. Then we've got a hydrogen here and a hydrogen there. So this has got 4 different groups attached, but only 3 of them are unique. So because it hasn't got 4 unique groups attached to that central carbon atom, then it's not chiral. Okay? Whereas this one has got these 4 unique groups attached. So that's what you're looking for. So you've only got 4 to choose from. So you should be able to do that. And I've eliminated 1. So you've only got to choose from 3 now. The next section is on cis-trans isomerism. So remember, cis looks like this because they're both the same side. You can imagine the hydrogens popping out here. So you've got the methyls the same side and the hydrogens the same side. And trans would look like this. Okay, so this is cis and this is trans. and I always think trans because it's transatlantic. You have to go across the ocean, so transatlantic. So you've just got to spot the cis-trans isomerism in this little setup here. Okay, so that's fairly okay. So have a whiz through that. In this next section, slight typo here actually. It says you've got to describe the bonding in methane. This should be ethene. So it's methane, ethene, and ethine. In terms of sp3, sp2 and sp hybridization. Now I know I went through this in class, okay, and I'm just going to whiz through it now just to just to help you remember. Just remember that sigma bonds are single, okay, and pi bonds are double, okay, and sp3, a rule of thumb is sp3 single bonds. If you see some double bonds, then it's sp2, and if you see some triple bonds, then it's sp. That's a quick rule of thumb. Methane, looking like this. Methane has got 4 hydrogens attached. All single bonds, so they're sp3 hybridized. That means that the s and the p orbitals on the carbon hybridized to form 4 new sp3 orbitals, okay, s3p hybrids, and they are in tetrahedral geometry. Once the carbon is hybridized, then the hydrogens overlap with these sp3 hybrid orbitals. That's the important point now. It's the carbon that hybridized. The carbon hybridized and the hydrogens overlapped. So that's what's happening there. With ethane, ethane's a different kettle of fish. What you've got there with ethane is you've got 2 carbons and you've got a double bond and you've got single bonds to hydrogen. What happens here is the carbons, each carbon will hybridize 1s and 2 p orbitals, okay? So 1 times s and 2 times p orbitals into sp2 orbitals. So it's put in 3 orbitals, so it'll get 3 orbitals out, 3 times sp2s. And they point out with a trigonal planar geometry. Okay, so this one, and one of these bonds here. Okay? And each one of them does it. Each carbon will do it. And they overlap. Now this last bond here, this purple bond I'm going to draw in here now, this double bond here, that's formed by overlapping p orbitals that weren't hybridized. Okay? The 2 orbitals that did hybridize, they overlap in the middle and they form the sigma bond. Okay? So they're the 2 sp2s, but the double bond comes from the unhybridized p orbital on each of the carbons. And that's what you've got to explain, okay? And then you can imagine that on the outside, once they've hybridized, then the hydrogens, these are these red, the s orbital of the hydrogens just overlap with these sp2 hybrids. and that's how ethene is drawn. That layered overlap on the top. So you've got a little bit of electron density above and below the plane. Okay, have a go at those and then have a go at triple bonds. Okay, we've got two things that we need to get through here. I'll deal with this number 5 first. Draw reaction profiles for both endothermic, exothermic and a catalyzed reaction. Okay, so we have reaction coordinate here. We've got energy here. There's our starting material, or reactants. There's our products. And what we've got is we'll have a little bit of activation energy and we'll go down to products. Now, this was the energy that we started off at. And this is the energy we've gone to. So, we've gone down in energy. In fact, we've had to lose some energy. And so this would be an example of an exothermic reaction. We started off at 10 and we've gone down to 5, so we've had to minus 5 units off. So we've got a negative sign there, so it's exothermic reaction. It's given off energy. It's gone to a new, lower, stable energy state. Now, from this space here, we had to collide the particles in order for them to react. So they've smashed into each other, and they have to do it with a certain amount of energy, and that energy here is this gap here from the starting material to the peak. The peak is called hashtag transition state. So this hashtag refers to a transition state. So this energy is called EA, which is activation enthalpy. So have a little go at that. Activation enthalpy. So we've got transition state, we've got activation enthalpy, we've got our delta H, this refers to, that's this bit here. We've got our delta H, and that's all for an exothermic reaction. So I want you to have a go at endothermic reaction and an enzyme reaction. This next one here, the one before that last one, it says, describe the physical properties of organic molecules including boiling and melting points. So boiling and melting points will basically be the same in relation to intermolecular forces of dispersion, dipole, hydrogen, and say what branching we'll have. Well, it starts off, if you've got a homologous series, it starts off, say for example, pick on this one first, CH4, methane. Then you could go to ethane. Let me draw that a little bit better. Then you could go to ethane, and then you could go to propane, butane, pentane, hexane, and so on and so forth. The chain is getting bigger. Okay. Now, when you're melting something first, so when you're going from a solid to a liquid, what you've got to do is put enough energy into the solid, in order to overcome intermolecular forces holding them together, so the chains would start to slide across each other. And then as you go in from a liquid to a gas, you've got to add a little bit more energy now to overcome all of the intermolecular forces to completely separate the molecules, so they'll go off into the gas phase. So each time you're looking at the energy requirements, okay, and the number of intermolecular forces which are going to be around. So it shouldn't come as a huge shock for you to see that as this chain gets longer and longer, so would the electron cloud around the chain. Now this is an alkane. And alkanes, they just have CHs, okay? So they've got no polar groups. Now they're fairly symmetrical. Symmetry there. Fairly symmetrical. And so they only have van der Waals forces, okay? Now, the bigger the cloud, the stronger the van der Waals forces. So the melting point and the boiling point will increase as you increase the chain length, okay? And that should make sense for you because they're going to have a bigger electron cloud and therefore more intermolecular forces to overcome, so they'd have to put more energy. And if you take temperature as an indication of the amount of energy that's going in, you would expect that this one down at the bottom would have more van der Waals forces and therefore would require more energy, so a hotter temperature than methane. So I hope that helps you with that somewhat, getting you started. Now what you need to think of is stackability. If I draw this 1, 2, 3, 4, 5, this pentane, I could imagine stacking lots of pentanes together. It would stack rather efficiently. However, if I take the same number of carbons now, an isomer, and I branch it, I could imagine that the stacking here with this branched alkane wouldn't be quite as efficient, and therefore branching will affect the boiling point and the melting point, and it's all to do with how they'll stack and how close the electron clouds are together. So go ahead and have a look at that setup. We've got some other considerations now. So we've just dealt there with alkanes, and that's a good way to start. The next thing that you need to consider is other intermolecular forces. Now these are going to come in the form of ketones, C double bond O's, amines, NH2s, carboxylic acids, and the reason why is because we're going to have hydrogen bonding, and we're going to have dipole-dipole bonding. What you need to find out now is, how does dipole-dipole bonding affect the melting and boiling point? Give examples. And how does hydrogen bonding affect the melting point and boiling point for a series, okay? For a homologous series. And how does that affect solubility? Now, when you're thinking about solubility, what you need to think about here is it polar or non-polar? And will it dissolve in water or won't it dissolve in water? And you could think of as, if you're dealing with alkanes, they're non-polar, so they won't dissolve in water. On the extreme, you could be dealing with alcohols and carboxylic acids, and these can hydrogen bond, so these are polar, so they may dissolve in water. But then you've got to think about chain length. So you've got to think about solubility as in, how long is the carbon chain and will it dissolve in water or non-polar solvents like hexane? And is there any functionality like this functional group and this functional group which will allow it to dissolve in water or not to dissolve in water and therefore dissolve in non-polar substances? You need to have a look at that. Okay, and just a brief description, I'd say no more than 200 words. Okay, so you've got chain length for van der Waals forces and branching for alkanes. Then you want to look at dipole-dipole for ketones, hydrogen bonding for amines and carboxylic acids, and then a discussion on solubility between non-polar and polar, and you should be done. Good. Okay, for this question, you need to work out which is a nucleophile, which is an electrophile, and whether it's an acid or a base. A good rule of thumb here is a nucleophile is an electron pair donator. So it's got some negative charge to donate, and an electrophile is a positively charged nucleus which can accept some electrons. So let's have a look at these. Br minus, so the negative charge means that it's got some electrons to donate, so I would expect that to be a nucleophile. We have ethene can donate those electrons, so that would be a nucleophile. We have Br plus, a positively charged centre, so I would expect that to be an electrophile. Water has a lone pair, was two lone pairs, and we know it can attack carbonyl groups because we get hydrolysis, so water would be a nucleophile. Okay, they can go out. We have H plus, which I think is an acid, and I suppose an electrophile. NH3 is structured like this. These are hydrogens, by the way. This has a lone pair, so it could be a nucleophile, and it's a base. This is an acid. We've got NH3 again, which is a nucleophile, typo by me. And BF3 can donate, can accept electrons, so this is going to be an electrophile. Now you need to explain why. The link is fairly clear, and you should just go and read. This is really simple combustion reaction, so you can do any alkane. Why not start with the simplest? Every combustion reaction is going to make CO2 and water. This is going to be a gas, isn't it? A liquid. Gas. Gas. Just balance that reaction now. So one carbon, 4 hydrogens, 2 hydrogens. So we need to put a 2 in front of there. So now we've got 4 hydrogens, and then balance the elemental oxygen last. So we've got 2, 4. So we need a 2 in front of that. So methane may be chlorinated by a photochemical reaction. Draw the appropriate stages. So there's initiation, propagation, and termination. Initiation is where we've got chlorine and we need to apply a little bit of light energy to split the chlorine up into 2 radicals. Once chlorine is split up into 2 radicals, we'd expect it then to go and attack the methane, and we'll get radical attack, so half an arrowhead, which is going to form the methyl radical CH3 dot plus HCl. Okay, then we could have the methyl radical reacting with a chlorine, to form our product, CH3Cl plus another chloride radical. And then we could have termination steps. We could have chlorine terminating with a chlorine radical. Oops. We could have chlorine radical and a methyl radical. and we could have 2 methyl radicals. 2H6. So we've got initiation, we've got a propagation step, and then we have got a termination step. And actually, and just check the propagation step, check if there's one more. This question was really an exercise in doing some research, which I know you all love. Now, these are important reactions. There's certain functional groups like the alcohol and the carbonyl group which are really important in organic chemistry, and knowing those reactions and knowing which sort of starting materials and reagents to use is really important, and it's something you've got to learn and you build up over time. And so what I'm suggesting here is you actually follow the web link which I sent you to and write down the reagents. Now all I want you to do, for example, is to write down the number. Now you've got to understand that you've got reverse arrows. So this first arrow is saying what will make an alkoxide salt, and the second arrow is saying what can I use to change an alkoxide salt back into an alcohol. Okay, so we could say, let's give an example, ketones. So let's say alcohol to ketone, if we were going to do that. So first off, what could we do for a ketone to make an alcohol? Now there's 2 reagents we could do. So ketone is basically looks like this. Okay, and we want it to go, so we want to take this ketone to look like this, which is an alcohol. So what we've done there is we've reduced the alcohol. So we need a reduction agent. So there's 2, lithium, aluminium hydride. Well, there's more than 2, but there's 2 that we've done about. And sodium borohydride. Okay? So look down your list and you'll find that lithium aluminium hydride is 7, so reagent number 7, and sodium borohydride is reagent number 8. Okay? So we've reduced our ketone to an alcohol. So now we want to go in the reverse direction. So if it's reduced in the first direction, then we want to oxidize in the reverse direction. So our oxidation agents for ketones would be Jones's reagent, which is number 10. And we could also use potassium dichromate, which is number 9. So ketones can be reduced to alcohols using reducing agents, and alcohols can be made into ketones using oxidation agents. This is really an unfailable question, as in I gave you the link of where it's from. So go ahead and do some research. Okay, if you got to this point, you're doing well in one sitting. The next point is we've got these reactions. So we've got alkynes, some reagents, and what the question's asking is what is the product? So we want to draw the product for all of these reactions. Okay. So we have got Lindlar's catalyst and we've got an alkane. Now these are classic hydrogenation reagents. So what we're going to get there is we're going to get some sort of alkene. And we've only got 2 carbons to start. So we must make ethene. So that's pretty easy. The next one is we've got HCl. Now this is an addition reaction. So HCl is going to add across the double bond, so we're probably going to get one chloroethene. Okay, so these are the answers that I'm looking for. I'm looking for you to draw the structure, okay, or name the structure. Look up these other two reactions. They are not too hard. This is another addition reaction. So instead of adding HCl now, you're going to add 2 bromines across the triple bond. And these are classic conditions for adding water across the double bond. So adding H and an OH across the double bond. And then look up the final one. Really easy. Follow the link, you'll have no problem. In this reaction, you need to give the example of the ozonolysis reaction. Now, I think the best way to start is to always draw out the reaction as a whole first, so you know the starting material and you know your products. So you've got pentene here, so you're going to have 1, 2, 3, 4, 5 pentuene, so it's going to be in the 2 position there. You're going to add ozone, O3, and you're going to split these off into 2 products. And the 2 products are going to be oops, sorry. The 2 products are going to be a split across this double bond. Oh God, sorry guys. A split across this double bond here. So I'm going to draw out pentene again. Oops. We're going to split this double bond here. And when we split that double bond there, we're going to form 2 products. So we're going to have that is for this portion here, so that's that methyl group. Let me just change colour. That's that methyl group there. That's the carbon there, and this is the hydrogen. Oops, which I haven't drawn very good there. So that's the hydrogen there. So we split that. That's that portion accounted for. The next bit will have a tail. So you've got that carbon, this carbon and this carbon. This carbon here is this carbon here. And you've added the oxygen across the double bond. Okay, so your 2 products are going to be two aldehydes, ethanal, and 1, 2, 3 propanol. Okay, so go ahead and find the mechanism now. The mechanism for a ozonolysis reaction. I'm going to draw out the general mechanism, and then you can work out the rest yourself. The mechanism for the ozonolysis looks the same. It's very long. It's a little bit complicated, but it's worth going through. So you start off with your alkene. Now I'm going to draw a general alkene and ozone. So what we've got here is attack on the double bond. This attacks this oxygen. So this oxygen attacks the double bond opens up, attacks this oxygen here, and this double bond quenches this positive charge here. So then this will form R. There's our original structure. Now we joined with this oxygen. This was already ozone, and this oxygen joined to this carbon here. This is an unstable structure. Immediately breaks down. So it forms 2 products. R. Now that oxygen with a negative charge, because these electrons now have been placed on this oxygen here, and this split up now. This bond here split. When we drew this arrow, it's split up, so we've got R, so we've got an aldehyde. Now these adjust, so I'm just going to turn one of these around now. So now what we've got, so we should run a positive charge. Now what we've got here, we'll have R, O, O minus, so all I've done now is just move the structure around. So we get attack again. Okay, and then what we finish off with there is we have a bit of dimethyl sulfide around. This attacks this oxygen here, which forms R, O, O minus, O, S, okay, so I'm going to label these through. Actually, I should have done this at the beginning. R1, R2, R1, R2, R1, R2, that's R1, that's R2, R2, R1. Okay, so we've had attack of the dimethyl sulfoxide, so that's a sulfur with two methyl groups on. This attacks this oxygen, cleaves this bond, so we're left in this state here. And then what we get is reorganisation. So this negative charge, I've gone one carbon too many here, so let me just rub this out. Oops. It's the same here, there should just be one bond to this O minus there. So this is a negative charge, so this comes in, cleaves this, cleaves that, and leaves us with R1 carbon double bond oxygen. We'll assume this is a hydrogen. Now we're concentrating on this bond here. So what we got is this bond cleaved and went into this oxygen here. So oxygen, double bond. This was connected to this R group here, this R2. And then this bond here, this cleaved and this charge went onto this oxygen here. So that left us with O minus, because that's that charge going onto the oxygen there, bonded to a sulfur with two methyls. There's the two methyls, there's the sulfur. Okay, so there's our aldehyde 1 and our aldehyde 2. Hope that's okay. A bit confusing. If you go to the link, it's much clearer. I'm just doing this offhand, so. This question here, this is asking for the product, so no mechanism here, just wants you to literally draw the product of the reaction. This here, NBS, and this HBr, you could think of this as introducing Br2 into the reaction. Okay, so really what you've got is a reaction between an alkene and Br2. Okay, so that's, you just draw the product, and it's an addition reaction. So you're going to add Br2 across the double bond. Draw the product in there. Now for this reaction here, what we've got to come up with is conditions by which we have gone from this alkene to this alcohol here. Okay? What's happened here? So what's happened is, this double bond, it starts off double bond, so at the end it's got CH2. It's got a CH2 there, and it's got 2 carbons. Now that's the ring goes on then, yeah? So this here is just a carbon. And in the product, what's gone on is the CH2 has gained another hydrogen. I'm going to draw that hydrogen in red or pink. So it's gained another hydrogen because it's gone from a CH2 here to a methyl group. So there's a CH3. And it's gained an OH at this point here on this carbon, which I'm going to draw there. And there's the rest of the ring. So we have added OH and H. We have added an OH and a H, or H2O. So this is a hydration reaction. Sorry, I haven't got used to writing with this pen. This is hydration, adding water across the double bond. So you're looking for conditions at which add water hydration reactions across a double bond, hydrating an alkene. Something to do with mercury acetate, I think. So look that up for that reaction. 14. For this reaction below, draw the product of the reaction. So you're looking for a structure again. This is an alkoxide. So this is effectively O minus. O minus is a nucleophile. Bromine attached to a carbon, that's a polar bond. So this is effectively delta plus. Okay? So we're going to nucleophilic attack. And what is the product of that reaction? That's for you to find out. Okay, for this question here is again, it's looking at reaction conditions, and if you answered the question earlier, and we did do the question earlier, we've got an alcohol, and if we turn an alcohol into a carbonyl group, then we're oxidizing. So we need reagents for oxidation. And the example I gave you before was Jones's reagent. Go and look up the conditions for Jones's reagent, and that will be the answer for that question there. Okay? Don't just put Jones's reagent, go and look up the conditions. 16. For the reaction below, draw the conditions of the reaction. Yeah, okay, doesn't look good. So we've got an alcohol again going to a ketone. We're oxidizing again. What are the conditions for oxidation? Next one below this, for the reaction below, draw the reaction to conditions. For the reaction, sorry about this is atrocious, isn't it? We have got a carbonyl group being reduced to an alcohol. So what are the conditions for reduction? Right. Not just sodium borohydride, go and find out what else we have to add to the reaction pot. Okay, so we've got cyanide attacking a ketone, and it says draw the product of the reaction. So we've got nucleophilic attack on a ketone. There's our ketone. There's our cyanide. Comes in, attacks the ketone. Ketone opens up. We form our tetrahedral intermediate. O minus. Because those electrons have gone up to sit on the oxygen, so that's them. Plus the cyanide that we've just added, that negative charge has attached itself in the form of a bond here, and then we'll get some protonation. So we're going to have OHCN, 2 methyls. So we've got a cyanohydrin. that's the general reaction. You just need to add it for the reactant that we've got there, because we didn't start off with this ketone, we started off with something else. So have a go at that one. Right, next one. For the reaction below, draw the product of the reactant. So we're starting off here with an ester, and if we were going to name this ester, this is just something extra, we name this chain first, the alcohol chain, so it's ethyl, and then we name the carboxylic acid next, which is 1, 2, 3, 4, ethyl butanate. So whenever we get the conditions, just get rid of that. Whenever we get the conditions of H plus and H2O, this is hydrolysis, so that's right, hydrolysis, water splitting. So we're going to split up the ester into two functional groups. So I'll draw the general reaction. We cleave along this bond here, okay, and we're going to add some H2O. When we cleave along the bond here, will leave us with two fragments. I've cleaved, so first off I've drawn this fragment, and then I'm going to draw the second fragment. Now we've cleaved it with water, so we need to add the elements of water across it, and we're going to add them as an H and an OH. The OH is there and the H is here. So you always cleave off the alcohol portion first and add a H to that, and then the carboxylic acid function. So we're going to leave us with a carboxylic acid and an alcohol. Okay, this is a two-stage reaction. We're going to take this benzoic acid and we're going to make it into this nitromethylbenzoate. Let's have a look what's happened here. There's two things that have happened. We've added a nitro group and we've added methyl to the end here, so we've made an ester here. So a nitro and an ester. And we've done this reaction in the lab. And what it's asking you for here is, for the reaction below, draw the intermediate product and the reaction conditions. We've actually done this reaction. When we did this reaction, we made this intermediate X here. And we made the ester, the methyl ester. First thing we did in the lab. Then we took X and we reacted. So we reacted X with a nitration mixture. So you need to go and find conditions for ester synthesis and conditions for nitration. And your X will be the ester, the methyl ester of benzoic acid. Very easy. So for this reaction again, you've got to find the intermediate product, so what's X, and you need to find the reaction conditions. These type of questions are really common in university. Now, sodium cyanide here is effectively a Cn minus nucleophile, and we had this reaction before, didn't we? We could get a TAC. So we could boot out the bromine, nucleophilic substitution. We're going to substitute this cyanide, this bromine, for the cyanide, okay? So you've got to draw the product of that reaction. Then you're going to be left with a cyanide attached to this group here. You've got to somehow reduce the cyanide to an NH2. So you've got to find conditions to reduce a C triple bond N, a nitrile. Okay, I'm just come back from a break, so voice change. The next reaction here, what's the product of this reaction? So let's have a look. NaH is sodium hydride, and it's effectively hydride. It's effectively H minus. Very strong base used for deprotonating. So you have got an OH alcohol. Hydride will deprotonate the OH. So this will effectively leave you with O minus. Okay? So if I had an O minus and I had also had a carbon with a bromine group attached, as we have here, that O minus could then come in and attack. So you need to draw the product of that reaction. It's going to be an epoxide. And just have a think what epoxide it could be. An epoxide is a carbon, carbon, carbon here, carbon here, with an oxygen in the middle. So that's that reaction. Okay, for this reaction you have to come up with the starting material here. So X here, what is X? And this is sodium azide, which is Na+, there's the sodium, and nitrogen, 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 plus, minus. So this is a nucleophile, and the nucleophile, what you're going to get, if I look at this sodium azide product here, I've added sodium azide. So if I chop here, my X is going to be 1, 2, 3 carbons, and the azide, this negative, will attack a carbon, so I need something attached to that third carbon. It could be any halide, and then that way the sodium azide will attack like this, and you get nucleophilic substitution. So my first compound is going to be a haloalkane. You've got to choose what haloalkane it's going to be. It's going to be a 3-carbon haloalkane. Once you've got to this azide product, then you've got to find conditions Y. So what would you react with this in order to turn it into a amine? Okay, so you have a little crack at that one. Conditions to an amine. I actually think there's a carbon too many here, so I'll take that into account. 23, carbon too many. 24. So for this one, what happens here is, this is a good leaving group. This isn't so good leaving, so good of a leaving group. So what actually happens is, we get this formed first, this adjoins to the alcohol first. This makes this now a good leaving group, and the I minus from the sodium iodide, this is effectively I minus, a nucleophile, can then come in and attack. You have just got to draw the product in here. So the product of this attack, okay? It's a substitution reaction. Okay, if you'd have done your question from earlier before about the alcohols, you'd have answered this question. What we've got here is an alcohol being converted into a chloride. Now, the carbon chain's not touched, so that's fine. We've just got to find the conditions to turn an alcohol to a halide. And if you look that up, it'll be very specific. SO2Cl. SOCl2, sorry. Thionyl chloride you're looking for. Find the rest of the conditions for thionyl chloride. The next reaction is to find the conditions to turn an amine, which is this, into this nitrogen triple bond, which is an excellent leaving group. You are looking for this guy. Okay, so find the conditions that use this guy. What do we need to make this guy here? Okay. Okay, for this question, what you need to do, if you're going for pass, you need to just come up with the reaction conditions. Okay, so X, Y, Z, and A. If you find all of those reaction conditions, you will get a pass. If you want merit and distinction, what you're going to have to do is come up with the reaction conditions and the mechanisms, the full mechanisms for each step. And I would label them step 1, step 2, step 3, step 4, and take them one portion at a time. And the way to tackle this reaction is to work out what's going on. So first off, we've got an OH here and a bromine here. So we're starting with a bromine, and we need to convert it to an alcohol group. Okay, so we've got some sort of nucleophilic substitution there. We want to substitute Br for OH, so we need OH as a nucleophile. So you need to look for conditions where OH is a nucleophile, probably sodium hydroxide. But look for the full conditions, okay? Then the next step, and if you're drawing the mechanism for that, that's just simple nucleophilic attack. Yeah? SN2. If the next step, you've got your OH, and you're going down to a carboxylic acid, so you get an oxidation. And we did this earlier as well, didn't we? This is oxidation of an alcohol. So that smells like Jones's reagent, and draw the mechanism for that, and we've done that in class, so you should be able to do that. Next step, you're going from a carboxylic acid to an acyl chloride. This is the only thing that's changing, okay? And this is similar conditions to the last reaction we did on the last page, which was with thionyl chloride. So look up those conditions there. Step 4, we've got an acyl chloride, which is a great starting material for making peptides on amide linkages. So if we look what's happened here, this is the product we want to make, and the only thing that's different is this bond here. So if I cleave this bond here and look at the two fragments, I've got a benzene ring and I've got an NH. So we've got a methylamine and we've got what we started off with, thionyl chloride. Okay? So methylamine, thionyl chloride, what are the rest of the conditions and what would be the reaction mechanism if you were going for a merit and distinction? Okay? Not such a bad one then. Okay, we want to tackle this question in 2 steps. So from the reactions above, give me an example of an addition reaction. Well, we could do bromine, an alkene attacking bromine, and you finish it off. So that would be my answer for that, an addition, because you're adding bromine across the double bond. Hopefully the final product will look like at this. Where you've added 2 bromines across the double bond. That would be what you'd want. Just get rid of that. So that's easy. Addition reaction is really easy. The next stage is to summarise the factors and conditions that influence haloalkane reactions, ensuring that you include SN1, SN2, E1 and E2 mechanisms. My strategy for this was to take one reaction at a time. So take SN1 first, then go on to SN2, then go to E1 and then E2. Remember that I gave out you that decision matrix. If you explain that, that would be great. Basically what you're looking at here is solvent, whether it's polar, non-polar, protic or non-protic, which is not called non-protic, it's called aprotic. You're looking at sterics, which is space, if there's any steric hindrance. And you're looking at the type of nucleophile. Okay, so in each case, if you explain each one of these for an SN1, SN2, E1 and E2, you will answer that question. Okay, so just take one in each turn. In this question, it says, explain the reaction that you might see. What it's asking for is it SN1 or is it SN2 and why? So, what we've got here is primary haloalkane, okay, primary haloalkane with just hydrogens, so not a lot of steric hindrance, and we've got a nice nucleophile here, a nice hard nucleophile, OH. It's going to come. Something went wrong with the video then. But what we've got is we've got a primary haloalkane, or OH, that will come in, attack this carbon here, which has been polarised because the bromine is at electronegative, so this is slightly positive, attack this carbon, cleave this bromine bond, all in one step, to form this alcohol. This is an SN2 reaction, because both particles, the bromomethane and the OH, are required in one step. This second reaction is a tertiary carbocation. These methyl groups provide steric hindrance and they're electron donating, so this goes via 2 steps. First, a tertiary carbocation is formed, then there's attack of the OH, so this bond cleaves on its own to form the alcohol. This is the rate determining step here, the cleavage of the bromine to form this carbocation. So because there's only one thing involved in the reaction, it's an SN1 reaction. What this means is, this rate determining step is this is the slowest step of the reaction. So there's the 2 different mechanisms. For this, it's asking, is it E1 or E2? And what's the product? Well, the product is both an alkene. So, with this one here, bulky base, so you're not going to get nucleophilic substitution, that's the first point. One of the hydrogens here on this carbon is deprotonated, base minus, and this causes the elimination of bromine. It happens all in one step, so it's E2. With this one, this bulky base can't get near here, so it's not nucleophilic substitution, and also it can't deprotonate directly, okay, because there's no hydrogens there. So it forms a tertiary carbocation, and then there's deprotonation to form the alkene, and that's because there's steric hindrance and it can form a stable tertiary carbocation. So this is E1, this is the rate determining step. Only this is involved in the slow step, so it's an E1 mechanism. Right, hopefully you find this useful.
Made with Doodlecast Pro.